Hello and welcome back. So in this particular video, we're going to make the idea that we've sort of established for conditional probability a little bit more abstract, so that way we can derive the conditional probability formula. Okay, so far we've only really used visual things to help us understand. We've used Venn diagrams, we've used dot diagrams to help us sort of understand the concept of conditional probability, and that is essentially restricting the sample space, okay? So you're restricting the number of outcomes that you have. However, what I'm going to do today in this video is I'm going to use tree diagrams, a concept that we're familiar with, all right, and this idea of dependent events to help us establish the formula, okay? Now, dependent events is essentially conditional probability anyway, all right? So have a think about it, all right? With our dependent events, the probability of the second outcome occurring is dependent on the first outcome occurring, right? So the probability of outcome two given outcome one occurs, okay? So that's why we can essentially sort of marry up this idea of dependent events with conditional probability to help us sort of formalize our rules. So let's have a look at this example. We have 3 red balls and 2 blue balls in a bag. A ball is taken without replacement, so that means we don't put it back in, making this a dependent multi-stage experiment. All right, and then a second ball is taken. It says draw a tree diagram to represent this problem. All right, let's discuss what this means for conditional probability. Okay, now I've already drawn the tree diagram up. We have 2 outcomes, red or blue, and 2 stages. All right, so first draw and second draw. Let's have a little bit of a think, all right? We have 3 out of 5 for red. Okay, we have a 3 in 5 chance, which also means that we have a 2 out of 5 chance for blue. Now, we've done the first draw, we haven't put anything back in. So for the second draw, we only have 4 available to us. And that happens for each of these. But each branch sort of matters depending on which one that we do, okay? All right. So if I've drawn a red out, okay, looking at this particular one here, if I have drawn a red out, that means I only have 2 reds left out of the 4 remaining in the bag, but I haven't touched blue, so we still have 2. However, if I go down this particular column, all right, I still have all 3 reds left in there, okay, but I now only have 1 blue left in here. Now, I'm not going to worry about calculating all of these different probabilities, but I do want to use this to sort of highlight something for us. So let's just pick just a single branch off of this tree. We're going to pick this one here. We're going to go up along here. So we draw a red first, then we're going to go down along here, and then we draw a blue in the second. Okay, let's use some notation here for us to sort of understand what this means for conditional probability. Right here at the very end, after we've gotten to the end, we've gone along our branch, which means that we multiply. Sorry, I lost my voice there for a second. Okay, remember when we're multiplying, this is essentially us finding at the very end, right, the probability of red and blue. Okay, that's essentially what's happening. But let's break down each individual stage, right? So our first stage here, all right, this particular thing here. Well, this particular branch on our probability tree, that's simply the probability that we draw a red, okay? Straight up with no conditions imposed. But what we really want to look at is what is our notation that we're going to use here? Well, this here is the probability that we draw a blue given that we've already drawn a red here. So let me just write that in our notation. The probability that we draw a blue given that we've already drawn a red. Now, remember, what do we do when we go along the branches? We multiply, right? So if I wanted to get to, I'll just write this up here. It's not really important for the answer, just so you understand what we're doing. The probability of red and blue, okay, in that order, is equal to 3 out of 5 times 2 out of 4. That's what we would normally do. But let's change the notation a little bit. What we're going to do is we're going to write this a little bit more formally. Let's do this in orange. We could also write this as the probability of red and blue is equal to the probability of our red, okay, so our initial sample of red, multiplied by our probability of our blue. given red. Okay, all right, that's essentially what we're doing here. Now, this actually forms the basis for our conditional probability rule. Okay, now imagine if we made this events A and B. This is such a cool formula. Okay, all right. If we made this as events A and B, which is essentially what we've just done above, all right, we can actually rearrange this to get the conditional probability formula. All right, now this is only for dependent problems. Okay, so just be aware. All right, if we rearrange this formula and we take P of B the other side and we divide it, we end up with this formula. All right, and this is the conditional probability formula, right? This needs a big red box around it in your books because this is so important. Note that the order matters. If I do P of B given A, it's equal to the same thing on top, but with P of A on the bottom. Remember, this can go in any order, A and B or B and A, it doesn't really matter, okay? But the thing that does matter, all right, is that the thing that comes after, right, the given condition usually goes on the bottom. That's what you're restricting your sample space to, all right? So just understanding this, all right, if you put this in terms of our Venn diagrams, okay, this is the thing that restricts our sample space. All right, our denominator restricts our sample space. Think back to our Venn diagrams. Okay, and this is calculating the probability of the intersection. If you go back and you use this formula on the previous examples that we've done with the Venn diagrams, you'll show that you'll get the exact same answers. It's really, really, really cool. Okay, all right, let's have a bit of a play with the actual formula so you can see what happens. Okay. Okay, sometimes you'll be given examples where you can't use a Venn diagram, you can't use a tree diagram, you can't use really anything. You just have to use the formula and your understanding, okay? Here is an example of a basic problem that uses that. Now, Lara is an athlete who enters a swimming and a running race, okay? So we're gonna have two events. Now, I've already defined the events below, we'll talk about that in a second. She has a 44% chance of winning the swimming race and a 37% chance of winning both. So that's winning both running and, pay attention to my words there, swimming. Find the nearest whole percentage of probability that she wins the running race if she has won the swimming race. Okay, so let's do a little bit of work here, all right, to understand what's going on. Okay, so I've gone ahead and defined my two events. I said let R be the event that Lara wins the running race. This is just to help us with our notation. And let W be the event that Lara wins the swimming race. What the question is actually asking us to do, if you have a look at our last sentence, okay, is find the probability that she wins the running race, given that she wins the, that she wins the swimming race. We might change, instead of that being a W for winning the swimming race, we might make that an S, okay? All right, so using our probability formula, remember, P of A given B is equal to P of A and B all over P of B. All right, let's match this up. So we know that we're going to need the probability that she wins the running and swimming over the probability of whatever thing is here, goes on the bottom, over the probability that she wins swimming, okay? Which is great. We're given both of those. All right, let's have a little bit of a look, right? She has a 44% chance of winning the swimming race. So this is 44%, all right? And then she has a 37% chance of winning both. 37%, all right? What I do is I would calculate this and put it into decimals, all right? So 0.37 over 0.44, okay? And now, after you do a little bit of simplification, you'll end up with a pretty horrific little decimal, all right, if you put this in your calculator, of 0.8409 ... which if you multiply by 100, you'll get a percentage, okay? Rounding to the nearest whole percentage, you'll end up with 84%. percent nearest whole number. Okay? All right. So just understanding what's happening here, let me just break this down. We've just used the conditional probability formula. All right. We used the probability that she won both races divided by the probability that she won the swimming race. Now that's where we're restricting the sample space again. Okay. We need to keep reminding ourselves that that's actually what we're doing. All right. We were given that she had a 37% chance of winning both races. So, oops, sorry. Okay. 37% chance of winning both races. All right. And then a 44% chance of winning the swimming race. Okay. And then it's just a matter of numbers game from there on out. Okay. I hope you found this helpful. This is the idea behind conditional probability. In our next series, what we're going to do is we're going to have a little bit of a look at using tree diagrams with conditional probability. Okay. All right. Thank you very much.